When you sing a song into a mic, it converts the changes in the air pressure into changes in electric current. Now, if you attach this to a speaker, then it converts these changes in the current back to sound. But you will probably hear nothing. And the reason for that is because this current produced by the microphone is very tiny, causing extremely tiny vibrations, and as a result, you will hear nothing. But if you could somehow increase the strength of the current over here and keep the pattern exactly the same, and now since the current has increased, the speaker will vibrate very nicely, and since the pattern is exactly the same, you'll pretty much hear his voice and his song. So in order to make this thing successfully work, we need a device in between that increases the strength of the current, but at the same time keeps the pattern exactly the same. Such devices which do that are called amplifiers. And usually these amplifiers are found inside the speakers themselves. Now, earlier amplifiers were big and bulky, which made our speakers, our devices big and bulky. So in order to build, let's say, a pocket radio, or maybe to build headphones, we needed to make tiny amplifiers. And it was this trio, Shockley, Brattain, and Bardeen, working at Bell Labs, realized the key to building a very tiny amplifier was using doped semiconductors. And after a lot of research and experiments, they finally invented the first semiconductor amplifier in around 1947-1948. So let's find out what they did. Their idea was to use an N-type semiconductor with a lot of electrons and sandwich in between a P-type semiconductor with very few holes, like this. Or another thing that you could do is take a P-type semiconductor with a lot of holes and sandwich in between an N-type semiconductor with very few electrons. They called it the transistor. The transistor. And we'll see the reason behind this name in the future videos. But since this material has N over here, then it has a P, and it has an N-type again, we call this as the NPN transistor. And similarly, if you look at this one, you have P, this is the P-type, then the N-type, then again the P-type. We call this as the PNP transistor. And the key to working of this is that this middle region, that's the key actually. This middle region that we have, the P-type here and the N-type here, it should satisfy two conditions. One, it has to be very thin, and we'll see why in a minute. It has to be very thin. And two, it has to be very lightly doped. Very lightly doped. As you can see, the doping here is much smaller than what you have over here. Same thing over here. We'll see now that under such circumstances, these things will act like an amplifier. So we can look at either the NPN or the PNP. Let's look at NPN and see how it can act as an amplifier. So here is our NPN transistor. Let's begin by attaching a power supply across its ends. So let's put some metallic contacts. And let's say we attach the positive of the power supply here. Let's say about 5 volts. So plus 5 volt. The negative, which is usually the ground, we're going to connect that over here. This is the ground. And by the way, I'm not showing the power supply. If it was a real circuit, a practical circuit would be like this. You would have a positive of the power supply here, the negative of the power supply right over there, and that would be connected over here. But I'm just ignoring this part of the circuit. It's there, of course, but I'm ignoring that so we can focus more on the transistor action. So what do you think is going to happen? Just pause the video and think about this. Well, since we have a positive over here, we might expect the electrons to get pulled out like this. And we might have a current over here, electrons flowing like this. But in order for that to happen, the electrons must continuously flow from this region into this region as well, right? We need electron flow everywhere. But can the electrons from this region flow into this region? The answer is no. And the reason is, remember that at every p-n junction, there is a depletion region, which acts like a barrier for the flow of majority charge carriers. The electrons are the majority over here. They really like to flow from here to here due to diffusion, but the barrier prevents them. And as a result, since these electrons can't flow from here to here due to the barrier, these electrons can't get pulled across, and there will be no current in the circuit. And regardless of what voltage you put, even if you put a 10 volts or a 15 volts over here, You don't expect any current, so there'll be nothing. Now, if you really want a current, you know what we could do? We could attach another terminal over here. We could attach another terminal and put another circuit over here. Say we apply a positive to this. Again, I'm not going to draw the entire circuit. I'm just going to draw the positive to this. Let's say we put about a positive 0.7 volt over here. And we'll see in a while why I'm choosing 0.7 volt. What do you think is going to happen? Again, pause the video and think about this. Well, now if you look carefully, notice the P is connected to more positive than this N. This N is grounded. And as a result, we are forward biasing this junction. So if you take this junction is being forward biased. And similarly, if you look at this junction, notice the N is connected to more positive than P. And as a result, this is reverse biased. This is reverse biased. And now remember that when a PN junction is reverse biased, it doesn't allow the flow of majority charge carriers. And so these electrons and holes can't flow across. But this junction is forward biased. Under forward bias, the majority charge carriers can flow across. They can diffuse into each other. And guess what? If you remember, for silicon, if you hit 0.7 volt, that's when the depletion region vanishes. And as a result, these electrons and holes can now easily diffuse into each other. So let me show that. So these electrons will start diffusing into the P. And of course, these holes will also diffuse over here. But I'm going to neglect the holes because they're very tiny in number anyways. Now the question is, what's going to happen to these electrons? And now we're reaching the climax of the transistor action, all right? Notice that these electrons can either be pulled out from here because of the positive, or they can be pulled out from here because of the positive here. What's going to happen? Well, remember that whenever we have a forward biased PN junction, in order for those electrons to get pulled out, they have to undergo recombination. We have spoken a lot about this in previous videos, so if you need more clarity, it would be great to watch that. But anyways, in order for the electrons to get pulled out, they have to undergo recombination. And the recombination chances over here in a transistor is very, very small for two reasons. One is because this P region is very lightly doped. So there are a small number of holes to begin with. And as a result, the recombination chances are small. But the second reason is that this is very thin. And as a result, most of the electrons that get injected over here will find themselves already at this end. And as a result, they can now be pulled by this voltage. You can also think of it this way. You see, when they're reaching this junction, because it is reverse biased, remember reverse bias doesn't allow majority charge carriers to flow through, but they accelerate minority charge carriers, right? And these electrons in the P region are the minority charge carriers. So because of the electric field, they get accelerated and they get collected over here, and then they can, flow through the terminal over here. So what's happening over here is that most of the electrons which get injected will just come out from here, and only a fraction of them will get recombined, and as a result they get pulled out from here. So if we were to put some numbers, we could say about 100 electrons are being injected per second. 100 electrons are injected per second, and maybe due to recombination only one electron is being pulled out from this terminal. So one electron per second. And as a result, about 99 electrons get pulled out from here. 99 electrons get pulled out from here, which means the current in this wire is about 99 times the current in this wire. And you may be like, well, what's the big deal? Well, the big deal is, let's think of it this way. You see, in order to pull one electron from here, when we try to pull one electron from here, about 99 electrons gets pulled out from here, right? That's the way we can think about this. Well, now imagine if we increase this voltage and try to pull more electrons from here. Let's say I tried to pull 2 electrons from here. What will happen? Well, we have the statistics here. We've seen that almost out of 100, 1 gets pulled out. So in order to to remove 2, about 200 will get injected. They have to get injected, right? You're increasing the forward bias voltage, more will get injected. About 200 will get injected. 2 comes out from here. That means 198 will get collected over here. That means notice when you double this, this also has doubled. And if this were to triple, this would be triple. If this were to half, this would be half, and so on. In other words, if the current in this wire fluctuates, the current in this wire would fluctuate in exactly the same manner. However, the current over here will always be 99 times more than the current over here. In other words, the current in this wire is the amplified version of the current in this wire, and that's exactly what we needed. And so if you want to use this to amplify your sound, then you can connect your microphone wire over here. Now, the microphone will be the one that will provide the voltage over here needed to forward bias this junction. And the voltage provided by the microphone will depend upon the sound. If your sound is very loud, this voltage will be high. If the sound is very low, like you're whispering, the voltage will be very low over here. Of course, the engineers will make sure that the voltage over here will never go below 0.7 volt and all of that stuff. But don't worry, this voltage will fluctuate pretty much depending upon your sound. And as a result, the current in this wire will also fluctuate depending on your sound. Now guess what? The current in this wire will fluctuate in this exactly the same manner as the current fluctuates over here. That's what we saw. But it is 99 times more, so it's amplified. So if you feed this now to a speaker, then in the speaker, the sound generated will be much louder than the sound that you're producing over here, but the pattern of that sound will be exactly the same because the fluctuations are exactly the same, which means that sound will be exactly like your voice, but it'll be much louder. And that's how a transistor can be used as an amplifier. Let's talk about the names that we give to the different parts of a transistor and also talk about some design-related details about it. We will take NPN transistor as our example, but the same will hold true even for a PNP. So we'll just take one example and work with it. Now, the names given to these three regions are really based on their functions, what they do when you take your transistor and make it work like an amplifier. In a previous video, we've seen how this transistor can behave like an amplifier. And so if you need some refresher, it would be a great idea to go back and watch that video and then come back over here. But we saw in the previous video what we did. We made some connections. We connected this side to the ground. We had connected this side to, I don't know, I think about a positive of 5 volts. Any voltage is fine here. And over this side, we had connected about positive 0.7 volt. And to quickly recall what happens, you see because of the forward bias over here, the P side is connected to the positive, the electrons are emitted from this junction all the way into this junction. And before they have any time to recombine, because of very small amount of holes over here, most of them just get swept across and collected over here. That's because of the voltage, that positive voltage we have supplied over here. So based on that, we can actually see the names behind this. Since this is emitting electrons, we call this region as the emitter. So this is called emitter. And since this is the region that collects the electrons, we call this as the collector. And this thin region in between is called the base. So the three parts of the transistors are emitter, base, and collector. And notice, in order for amplification to work, if you want to make this work as an amplifier, then the necessary condition that the two junctions must follow is that the emitter base has to be forward biased. This has to be forward biased. And the collector base, look at what's happening to collector base. It is reverse biased because notice the N-type is connected to more positive than the P-type. So this junction has to be reverse biased. This is a necessary condition. And we'll see what happens if you don't forward bias this. If you reverse bias the emitter base junction, then majority charge carriers can't diffuse through, and as a result, these electrons will not get emitted, and nothing will happen. And similarly, the collector base junction has to be reverse biased because these injected electrons have to get swept across. They can only get swept across. Remember, these injected electrons in this region act like the minority charge carriers. In the P-type, electrons are minority. And for them to get swept across, we need a reverse bias. We've spoken about this in previous videos, all right? And similarly, if you had forward biased it, what would have happened? Well, if you had forward biased this junction, first of all, it would be hard for these electrons to get swept across. But more importantly, the electrons from the collector would start diffusing into the base, and as a result, the net flow of electrons from across upwards, from base to collector, well, that would be decreased, right? Because there'll be some flow this way, and there'll be some flow this way as well. And so we'll just mess up with our amplifier working. And therefore, we don't want this region to be forward biased. All right, now we may have one question in your head. Isn't the collector and the emitter identical? If we were to flip the transistor upside down, it wouldn't look any different. So what's the difference between them? Well, from the operation point of view, there's no difference. However, if you look from the design point of view, there are certain differences. And here's some of them. First of all, since the emitter's job is to, inject electrons into the base, we would like to dope the emitter very heavily. So emitters are always heavily doped regions. And the idea is the more you dope them, the more electrons get injected when you forward bias it, and so more electrons could get collected, and as a result, you would have more amplification. On the other hand, look at the base region. The base region we have already seen. For proper working of a transistor, it has to be thin, very thin, and lightly doped, very lightly doped. Okay, now what about the collector? Well, if you think about it, the collector doping doesn't really matter for us, right? I mean, look at in our amplification, what matters is how many electrons get injected, and that depends upon the doping of the emitter, and how many electrons recombine. That depends on this, right? The electrons that don't recombine will eventually get collected regardless of how many electrons are there in the collector. So strictly speaking, you can, whether you dope collector very heavily or you dope it very lightly, it's not going to affect our mechanism all that much. Now, having said that, there is one thing we need to take care of. You see, this PN junction is reverse biased. And we've seen before that when a PN junction gets reverse biased, if the voltage exceeds a particular value, it undergoes breakdown. That means a very high current starts flowing from N to P. We don't want that to happen. If that happens, that'll mess up with our amplification action. We don't want this junction to ever undergo breakdown when our transistor is working as an amplifier. So what we have to do is we have to make sure that this junction has a very large breakdown voltage so that it can withstand a lot of voltage before undergoing breakdown. Let's just quickly write that down. We need the collector base junction. We need the CB junction to have large reverse breakdown voltage. We usually call that as VR. So how do we achieve that? Now here's a simple way to think about it without getting into too much details. The lesser you dope this region, because this region is already very lightly doped, so the lesser you dope this region, the larger the breakdown voltage. I like to remember our Zener diode. Remember, Zener diode is very heavily doped, and under such heavy doping, it has a small breakdown voltage. That's a specialty. Well, lighter doping means larger breakdown voltage. So if you need more clarity on how that happens and how the depletion region gets affected, it would be a great idea to go back and watch that video on Zener diode again. But anyways, so to make sure that this reverse breakdown voltage is high enough, the collector is usually lightly doped. You get that? It's nothing to do with our operation of amplification, but just to make sure it doesn't undergo breakdown. So this is lightly doped. Now you may ask, well, how lightly doped is it? And this is not really all that rigorous. It depends on different transistors. It turns out that in some transistors, the doping concentration of collector is moderate between that of the emitter and that of the base. Well, in some other cases, it's seen that the collector doping is even kept smaller than that of the base. So there is no hard and fast rule, but what is important is that the emitter must be heavily doped and the base has to be thin and very lightly doped. The collector doping is only to ensure all these other design related issues, all right? So to make it visually more accurate, let me show a little bit less electrons in the collector compared to the emitter. One more difference between emitter and collector is in their size. It turns out that the collector is very big in size. All right, so to be more visually accurate, it would be better to draw our transistor a little bit big. And that's what you will see in most drawings. You will see that the collector is usually drawn bigger than the rest of the regions of a transistor. And again, this has nothing to do with the amplification action. It's again from a design point of view. The idea is roughly this. You see, we want the transistor to be big enough so that when the currents are flowing through it, it doesn't heat up very quickly. If it's very small, its temperature will shoot up very quickly, and again, we can have problems. Emitter, well, we can't make that region big because, we want to make it heavily doped. So it's easier to dope something very heavily if it's small. Base is anyways very thin. It has to be thin for our amplification. It's the collector that really doesn't matter how much you dope it. And since we are moderately or lightly doping it, we like to make the collector big. Another reason for collector being big is that's the design. So this is not what a real transistor, a practical transistor would look like. In reality, a transistor would look somewhat like this. You ready? Here it is. A real transistor looks somewhat like this. This is how the design is for a real transistor. So you again have the emitter. Notice how small it is. You have the thin base region. and you have this huge collector region, and the terminals are over here. So this will be encapsulated, and you'll have 3 wires coming out from here, so we can do our attachments. And so collector is usually moderately doped, and it's also one of the biggest regions of our transistor. In this video, let's look at the circuit symbol of a transistor. We've already seen that there are 2 kinds of transistors. One is the NPN, where a p-type is sandwiched between 2 n-types, and we also have a PNP transistor, where an n-type is sandwiched between 2 p-types. And in a previous video, we even saw what their names are. The different regions have their different names. We call the heavily doped one as the emitter. The very lightly doped thin region is called the base. And the biggest region of the transistor, which is usually moderately doped or even very lightly doped, is called the collector. Now let's look at the circuit symbol of this. The circuit symbol of a transistor looks somewhat like this. This way, like this, and like this. Ta-da, there you have it. This is how a transistor is drawn in any circuit. So you can see there are 3 regions. There'll be 3 terminals for a transistor, and these are the 3 terminals. So this one is the base. That's easily identifiable. This is the base. And one of these 2 is the collector, and the other one would be the emitter. Now, our symbol has to be a little bit better, because we should be able to identify which is the emitter and which is the collector, because you've seen they're not the same things. And we should also be able to identify whether we're dealing with an NPN transistor or a PNP transistor. So the way we do this is we put an arrow mark on the emitter head all the time. So if this is the emitter, we're going to put an arrow mark over here. If this is the emitter, we're going to put the arrow mark over there. So that's how we can identify which is the emitter. And the direction of the arrow mark is going to tell us whether it's an NPN transistor or a PNP transistor. So here's how we do it. If you look at an NPN transistor, when it's working like an amplifier, these electrons get emitted from N to P, right? And as a result, there's a current from P to N, right? Because electrons are negatively charged particles. So that results in a current. Let me use some color. Okay, let me use the green itself. So that gives us a current from P to N. And so if I were to draw for an NPN transistor, and let's say this was the emitter, what I would do is, let me just write that. This would be N, this would be P, this would be P, this would be N again. And if this is the emitter, I'm going to draw this P to N symbol over here. So I would just put an arrow mark over here. Ta-da! There you have it. So the arrow mark is telling me that this is the emitter. And if this is the emitter, this is the base, this has to be the collector. And by looking at the arrow mark, one can understand, oh, this is the p-type and this is the n-type. Therefore, it's a NPN transistor. So similarly, if we were to draw a PNP transistor, the circuit symbol would look exactly the same. I mean, pretty much the same. Okay, well, let's see. Okay, this would be the base. Let's say I want to make this the emitter, and this has to be collector. Now, if I want this to be PNP, this would be P, this would be P, and this would be N. Again, if we were to make this work as an amplifier, then notice the holes would get injected from P to N. The working is exactly the same. And as a result, we will now get a current from P to N. And so I'm going to represent that on the emitter led from P to N. So our diagram will look like this. And so that's how we can show the circuit symbol. All right, let's take a couple of practice examples. So we have 2 transistor symbols. Just pause the video and see if you can identify whether it's an NPN or a PNP transistor, and whether you can identify which is the emitter, collector, and base. All right, let's do it. Let's start with this one. The moment I see an arrow mark over here, I understand this is the emitter. This is the base. Base is easy to identify, right? It is the base. And here's the collector. And then I always remember that the current is always from P to N. Can you see? The current from the emitter to base is always from P to N. P to N and P to N. So the first thing I'll do is I know that this is P and this is N. Once I do that, well, if this is P and this is N, this has to be P. And so I understand, this is a PNP transistor. All right, let's do this one. The moment I see this, there's an arrow mark over here. I'm going to call this as the emitter. This is the base. This is the collector. Again, I remember the current from the in the emitter base is always from P to N. So it's going this way. So this has to be P. this is P, and this is N. And so N, P, N, yay, NPN transistor. And one last thing is that I was always curious as to what was the motivation behind this symbol for the transistor. And this picture might give us some answers. This is the picture of the world's first transistor ever built, or at least its replica. And this transistor looks a little bit different than what we have today. And we don't have to worry about how it works. These are obsolete devices. We don't use them today. But over here, you can see this sort of like a triangle thing over here. Well, this metallic wire was the emitter. This is just a metallic wire. This was the emitter back then. This another metallic wire you can see was the collector. And this emitter and collector, these two wires were pressing on. You can see some kind of a grayish thing over here. This was the germanium that they used. This was the semiconductor, and they call them as the base. And the semiconductor is lying on top of a copper slab or something. But anyways, you can sort of see, we don't have to worry about how this thing works, okay, don't worry. But you can sort of see where this symbol comes from, right? The emitter and collector are literally sticking to the base like what we have drawn over here. And this also tells us why the base was called the base. I mean, if you look at this modern transistors, like ones we use today, it doesn't make sense. Why would we call the sandwich layer base? But over here, it makes perfect sense. That was literally the base on which the emitter and the collector were stuck. So I think they devised the names and the symbol when this transistor were built. But once we improved the transistor, the name just got stuck, the symbol got stuck, and we thought we'll just keep them. Let's name the different currents through our transistor, find out what's the connection between these different currents, and also see what makes a transistor a good transistor. We'll explore some specifications of a transistor. So let's look at an NPN transistor, the same one that we have been working with for quite a while now. We've seen the different parts of these transistors. The heavily doped one is called the emitter, this lightly doped thin region is called the base, and the biggest region is called the collector. And we've also seen, in order to make it work as an amplifier, the connections that we do, we usually connect the emitter to the ground. Then we supply a positive over here, forward biasing this junction. And as a result, let's quickly recap what happens. Due to this forward bias, the depletion region here vanishes and the charge carriers can diffuse into each other. So the electrons over here, they diffuse into the base region. And since base region has a very tiny amount of holes, only few of them recombine with the holes over here, and as a result only a small fraction of these electrons can come out from the base terminals. And what happens to the remaining electrons? Well, because of the positive that is supplied over here, that positive starts pulling these electrons. You see the collector base is reverse biased because the N-type over here is connected to more positive than the P-type over here. And as a result, the remaining electrons will be swept across due to this reverse bias, and they will be collected over here, and they come out from this terminal. Of course, the electrons don't come out like this. They come out through the wire, but you get the idea. So what we'll do is we'll look at the different currents to the different parts of this transistor. Let's start with the current that we get over here. You see, because the electrons are flowing out of the base terminal, the direction of the current is in the opposite direction. So over here we would say the current would be in this direction, and we'll call that as the base current. The base current because it's coming out of the base terminal. Similarly over here, notice because of the electrons coming out from here, we get a current downwards. You see that? Electrons are going upwards, so the conventional direction of the current is downwards. So we get a current downwards, and we call that current as the collector current. This is the collector current. And now if you put some numbers, let's say about 5 electrons came out from here, and let's say about 95 electrons came out from here, from this wire. Then notice as the 5 electrons come out over here, they push these electrons because there's a connection over here, there's a circuit over here, and as a result 5 electrons get injected into the emitter from the external wire. And similarly, as 95 electrons come out over here, these 95 electrons get injected back, and as a result total 100 electrons are getting injected at the same time. And as a result, there is a current downwards over here, and we'll call that as the emitter current. emitter current. So these are the three currents that we have in a transistor. And if you look at these numbers carefully, we can even identify the connection between these three currents. So I want you to pause the video and just see if you can find out what's the connection between IC, IB, and IE. Well, one way you can see is that 100 electrons are going in, out of which 5 are going here and 95 are going here, which means if you add these two currents, you get this current. So let's write that down. The connection between the three currents is that IE, the emitter current, will be equal to the base current, which we'll show using green, plus the collector current over here. And you can also see it directly by looking at the direction of the currents. You can see that IC and IB are entering the transistor, and that total current entering the transistor should be equal to the current that's exiting the transistor. IE is the one that's exiting. However you want to do, this is the connection between the currents. And we can find more connections between the currents. For example, if you look over here, out of 100 electrons that got injected, about 95 electrons went through over here. And so we could say the collector current is 95% of the emitter current, right? So we can write that over here. For our example, we could say the collector current IC is 95%, which means 0.95 times the emitter current. And this number is usually represented as alpha. So in more general terms, we could say IC equals alpha. That number is called alpha times IE. In our example, this alpha is about 0.95. And that number is pretty much a constant for a given transistor. It only depends upon the doping levels of the emitter, maybe. It depends upon how thin the base is, how few holes, how many holes the base has, and all these design specifications is what decides the value of alpha. Higher the value of alpha, for example, if alpha is 0.99, that means 99% of electrons get through, and only 1% of electrons come out over here. That means the amplification is very high. So higher the value of alpha, better amplification you would get out of the transistor. And say if alpha was, I don't know, maybe 0.4, that would be a horrible transistor, because that would mean only 40% get through and about 60% comes out. That's pathetic. You wouldn't buy a transistor which has alpha value of 0.4. So alpha value is ideally very, very close to 1, very close, like 0.99 or 0.999 or something like that. All right, another connection that we would like to do is between the collector current and the base current. And the reason for that, the collector current is usually the output, because that's the amplified current. Let me call that. So this is usually the output. Let me use the same color. So this is usually the output in any application. And this base current is usually the input. This is usually the input. So we'd also like to have a connection between these two. And we can see that connection again from these numbers. You see, in our example, we could see that IC is equal to, well, how many times more compared to IB? Well, IC is 95, IB is 5, so 95 divided by 5 is 19. So we see that IC is 19 times more than IB, because 19 times 5 is 95, right? So we could say IC is, let's use this color, 19 times more than IB, And in general, this number is called beta. So usually you would see people writing it as IC equals beta times IB. And if you look carefully, if you know what alpha is, you can calculate beta, right? Because if you know alpha, then you get this, how much fraction go through, and as a result, you can calculate how much fraction comes out over here, and you can calculate what beta is. So strictly speaking, you only need to know one of these numbers, and you can calculate the other. And this beta is often called current gain. It's called gain because it's literally telling us how much is the output current gaining compared to the input. In our example, it is 19, but in a practical transistor, that number can go up to 200 or 300. And one last thing we'll do is find the connection between this alpha and beta, because we've seen that if you know one, we can find the other. So before I do that, I really encourage you to pause this video and see if you can do it yourself. All right, there are a couple of ways in which you can do that. One way, maybe you can just substitute these equations somehow into this equation and do that. But I like to do it more intuitively than that. So I like to think of it this way. Let's say about 1 million electrons, 1 million get injected from emitter to base. Or you can think of it as 1 billion, whatever you want. So let's take some large number. So let's say about 1 million. I'm just going to write the 1 over here. Then we know that only alpha fraction of it get through. That means alpha million will get through over here. Makes sense, right? If alpha is 0.95, only 0.95 million will get through. And the remaining will be collected over here. How much is that remaining one? Well, out of 1, if alpha goes through, remaining would be 1 minus alpha. 1 minus alpha will come out from here. And so from this, we can find what beta is. Beta, which is the current gain, is the ratio of the collector current and the base current. Can you see that? So it is the collector current, in our case is the alpha, divided by the base current. That's going to be 1 minus alpha. And there we have it. That's the connection between beta and alpha. And I don't remember this equation. Whenever I need this, I will always derive it this way in my head. And of course, you can also rearrange this equation and get alpha is equal to something in terms of beta. I leave that to you. So to quickly summarize, alpha and beta are two numbers that tell us how good or bad our transistors are. And they're not two independent numbers. If you know one, if you fix one, the other one also gets fixed. For a good transistor, alpha value is very, very close to 1, like 0.95 or 0.99 or something, and beta value is much larger than 1. Could be something like 200 or 300 or 500. And their value largely depends on the width and the doping concentration of this base region.